Good morning. Today we're going to do some revision on what we had discussed in the previous lectures. So we are going to look at the energy of a point charge distribution. This we did already in the previous lectures, but if we were to assemble some charge configuration, right? Let's say we have multiple charges, Q1, Q2, Q3, Q4, so on and so forth. If we have multiple charges like that, what is the energy required to build this configuration? That's what we're looking at. So the first charge itself, first charge Q1, you're bringing them from very far away to this location wherever you're assembling them. This is the location where you're assembling the charges. So when you bring in Q1 from outside, there is no charge here. There is no charge initially. Charge is equal to 0. So to bring in Q1 itself, it is free of cost as such, because there is no potential here to begin with, because there is no charge. But once I bring in Q1, then if I want to bring in Q2 from very far away and place this here so I can build this charge distribution, then there is a field that is created by this charge Q1. So then I have to take the potential of the charge here, right? So I can look at the work done. So the work done to bring charge 2 would be K times Q2, and you are doing this in the potential of the charge 1, Q1R. And so we can write this as R12 because that is the distance between the first charge and the second charge. So now if you put in Q2 here, and then now if you want to bring in more charges, let's say you want to bring in Q3, now Q3 will see the potential of both Q1 and Q2, so work done for 3 would be K times Q3, Q1 by R13 plus Q3, Q2 by R23. And we did this in the last lecture, and then we were expanding this so we can come up with a generalized term. And we did, add up all these works like work 1 plus work 2 plus work 3 all the way up to work n if we are assembling n point charges. And we saw that this could be expressed as half times sigma I is equal to 1 to n qi v of ri. So this V of Ri is simply K Q J by Rij. So for the ith charge, the potential is being caused by something before it. So for the third charge, we are counting first and second. For fourth, we are counting 1, 2, 3, so on and so forth. And in general, we showed that we can do the counting and we can do the double counting. That is, I can do both Q1, Q2 and Q2, Q1, and these are essentially equal. If you look at these products, so I can do both Q1, Q2 and Q2, Q1 and just take half of it so that the summation is a single summation so that I don't have to worry about duplicating the terms. So from here, then we saw that we can generalize this by making point charges infinitesimally small. We can rewrite this half of Qi V of Ri, where I goes from 1 to n, by making the point charges very tiny. Suppose if you take a continuous charge distribution, you can achieve this by dissecting this charge distribution into tiny cells, and each cell you can consider it to be a point charge, right? And if I consider that the volume density, charge density is rho r, that is the total charge density, and this small piece has a volume of dou tau, then the total charge in the small volume is that, right? So by doing that, we can write in general the expression as half of, instead of charge, now we would have charge density. V would be simply V, and you have a volume element d tau, so that you go over each of these elements to integrate to get the total energy. So now we can do a mathematical trick here. So we know from Gauss's law is essentially stating that the divergence of electric field is rho over epsilon naught. Then rho is equal to epsilon naught times del dot E. So here what we are saying is that the electric field that is there is essentially coming out of the charge. The charge is acting like a faucet, putting out, like how a faucet is putting out water, the charge is pumping electric field in a way into the plana surrounding it. And so that electric field is obviously proportional to the charge in that region. And that's what this is saying. So I can then take this and plug it in here. So then I can write this as half of epsilon naught is simply a constant. I have del dot E times V d tau. So notice that this divergence times V, we can get this. V is a function. It's not a constant. It's a function. It is, for example, it goes as 1 over r, so it's not constant. So you cannot pull it out of the integral. So let's hold on to this equation here. Let me call this as equation star. We'll come back to this equation star in a minute. Now let's look at a vector. Let's call this vector A. So this vector A is essentially it has a magnitude and direction, and then I have a scalar function f. This is not a constant. It's a function, scalar function, right? So I have a vector A x y z. So you can imagine some vector field where you have all these vectors, and one of these vectors I am calling it as A, and this is a scalar function f, which is also a function of x y z, right? So I am multiplying a scalar function with a vector A. So now if I want to take gradient of that, so if I want to take not gradient, I'm sorry, the divergence, because this is still a vector, the divergence of this, then I can write that as A times gradient of f. We're simply doing by parts, and or the chain rule, and f times divergence of A, right? First it operates on f, then it operates on A. So then now I can rewrite this f times the gradient of A, the divergence of A. I apologize, it's very easy to make these mistakes between gradient and divergence while teaching. So I urge you to be a little bit more extra careful, because sometimes I might write a divergence but say gradient, because I have to say gradient and divergence several times in the equation. So sometimes I may write the divergence but call it gradient, or write gradient and call it divergence. So please be careful there. I'll try to be more conscious too. This is the divergence of A. So I can write that as simply the divergence of FA minus A times gradient of F. The vector is on the gradient. So now if I perform a volume integral on these, right, I'm performing a volume integral on these. This is simply just the volume integral, so I'm going to write it as minus A times gradient of f d tau. But now look at this one. This is a volume integral. This is the divergence. It's a volume integral of FA over the entire volume. And if you recall, we have done in chapter 1, we have looked at the divergence theorem, or the Gauss's theorem, not Gauss's law, Gauss's theorem, where we saw that the volume integral of the divergence is simply equal to the surface integral, right, of j dot dA. So here I have the volume integral of a total gradient. So then I can write this simply as the surface integral of FA dot dA from Gauss's theorem. This is Gauss's theorem, not to be confused with Gauss's law. So the second term then, that is this term, can be written as simply a surface integral of FA dot dA. And this is the other side is F of divergence of A d tau. So we can get this by simply doing divergence by parts there, or chain rule there. So this we can use in the equation that we labeled as star, because here we have divergence of E times a function V, which is similar to this. So I can use this equation, let me call it hash, and then let's see what happens if I do that. So we have the total energy. We have the total energy to be epsilon naught by 2 divergence of E V d tau. This is the equation that we called as star, and then we derived another equation which is basically divergence of A times function d tau is equal to minus the volume integral. This is volume integral of A gradient of F plus the surface integral of FA dot dA. This we got from the divergence theorem, and this is the equation we called as hash. So now I can use this to expand this. So I would have epsilon naught by 2. Instead of A, I have E. So I have a negative here. I'm expanding this. So negative epsilon naught 2 integral E dot the gradient of V, right? And this is a volume integral, so d tau, plus the surface integral of F, which is V. A is the electric field E dot dA, but this is over the surface. Now we have a negative sign here and a gradient here. Negative of gradient V is how we define the electric field. So here then we have epsilon naught by 2 volume integral of E dot E over the volume plus the surface integral VE dot dA. Or this E dot dE is simply E squared. It's the dot product with itself, so you get the magnitude squared. So then I can write the total energy of assembling the charge distribution. So remember that we're looking at the energy of a charge distribution, right? I can write it as epsilon naught by 2 volume integral of E squared d tau plus the surface integral of VE dot dA. Now, what is the volume that we are integrating over? That's the question. If we ask ourselves, we are essentially integrating around. If this is our charge distribution, we're integrating around this charge distribution. But it doesn't matter even if you integrate, even if you increase your volume, because remember that we started out with the integral of half of rho of r v of r around the volume. So what we did was we had a charge distribution. We divided this into tiny cells, and for each cell we are asking this and integrating, and that's what this integral gave us after some mathematical manipulation. But essentially we were evaluating this integral. Now imagine there is no charge other than what you have within this boundary, right? Then even if I say, if I extend my integral space from the boundary, from the body to say this, the integral should not change, because if I consider a point here, there is no charge, so the integral is 0, right? I can even do this. I can integrate over this volume, and still the integral would remain the same, because all these parts around the charge distribution have no charge. So this rho of r in the integral is 0, so they don't contribute. So if you take, in fact, if you integrate over all space, then over the entire surface of that boundary, this term goes to 0. That is, this term is much bigger. It goes to 0 in the sense that it becomes much lower compared to this e square term. This e square term, the integrand is always positive, and if you integrate over all space, right? So this becomes much bigger. So we take this as epsilon naught by 2 integral over e squared by dv. So then you can see that if I take this epsilon naught by 2 inside, I would have epsilon naught e squared by 2 d tau. This is the volume integral. So this integrand is sort of the energy density, volume energy density. So this is the volume energy density. Now, where is this energy stored? How can we understand this energy? How is this energy stored? To do that, let's take a step back. Some lectures ago, we discussed the self energy of an electron. And before we discuss the self energy of an electron, we discussed how to construct a spherical shell of charge. So if I have a spherical shell of charge, I'm drawing the cross section, so it looks circular here. But what it is cross section of a sphere, a shell. So you can imagine this sphere, spherical shell in 3D. I'm only drawing the cross section, right? Let's say this is R and this is dr. We showed that there is no electric field inside this shell because now imagine that this is the spherical shell, right? This is a spherical shell. If I take a particular point here, then I can consider a cone of charge here like this that would have electric field pointing down, but by symmetry of the sphere there would be an equal and there would be an equal amount of charge below this point, but that would have electric field pointing up. So these two cancel out when you integrate over the sphere. So inside this there's no electric field. But outside this, imagine you are very far away. You're very far away at some distance r. Then from your point of view, because you are so far from the charge, this pretty much behaves like a point charge to you because you are very far. This r is much greater than the radius of the spherical shell. So you would see a field that goes like kq over r, where q is the total charge, which you can get by integrating the charge density over the surface of the spherical shell, right? So here, what we need to note is E inside the shell is not 0, and E outside shell is not equal to 0. So within the shell there is no electric field, but outside the shell there is electric field. So now imagine that you want to compress this shell. So you have a charged shell, and the charged shell has no electric field inside by symmetry, like how we have discussed. But if you are far from the sphere of charge, you should see an electric field because that pretty much behaves like a point charge to you. So electric field outside is not 0, but inside it is 0. So now if I were to imagine compressing the shell, when I compress the shell to, let's say, from R to R minus dr, let's say I compress the shell by dr, then what is happening is I'm going from a shell that's like this to a shell that is like this. I'm decreasing it by dr. Then this part where the shell previously was, there was no electric field there because that part was inside the shell. Now if I decrease the shell from R to R minus dr, in the space dr, this becomes outside the shell now, because now I have compressed the shell. So this part that I'm shading in red, after shrinking, after compressing the sphere to r minus dr, the shaded space would be outside the shell. So now there would be an electric field. So by compressing the shell, there is electric field coming in the shaded region because of that compression. So that is the potential energy that is stored there. And that's what this energy density is essentially implying, that it is energy that is stored that appears that you would see as an electric field if you were to compress this spherical shell. So now that said, let's talk about superposition. So we have defined the electric field energy as E square d tau. Now if I have two electric fields, E1 and E2, they're vectors, so they add like vectors, then E square would essentially be E1 square plus E2 square plus 2 E1 dot E2. So when you have the superposition of fields, you get this extra term of 2E1 plus E2. So the total energy then would be epsilon naught E1 square epsilon naught by 2 E2 square plus epsilon naught E1 dot E2, right? So so if you double the charge everywhere, you quadruple the energy, right? So if you double the charge, you get this extra term. It's not simply E1 square plus E2 square, but you do get this extra term of 2E1 dot E2 because electric field is a vector. Okay, so now let's go back to the example of the spherical shell so that we understand this energy a little more clearly. So if I have a spherical shell, again, I'm drawing the circular cross section. Then let's say this has a total charge of Q, right? The total charge of this spherical shell. This is a spherical shell of charge is Q. So now consider a Gaussian surface just outside the shell. So this is a Gaussian surface that we are considering. So from Gauss's law, if I do the integral of E dot dA over the surface, over this Gaussian surface that I showed by the dotted lines, then that should give me rho by epsilon naught, the charge density by epsilon naught. So then, or the total charge enclosed by epsilon naught. So then here we see that naturally there is a spherical symmetry, so we only have E along the radial direction, and dA gives us 4 pi r squared. This integral over the sphere gives the spherical area, the total surface area of the sphere, and ER. So if I have this Gaussian surface of radius r, then the integral would be ER times 4 pi r squared, which is equal to Q by epsilon naught. Right. So there you can see that we can write in this case the electric field itself as Q by 4 pi epsilon naught r square, right? Or we can take this 4 pi r square, Q by 4 pi r square, and call it sigma. That would be the surface charge. You're dividing the total charge by the surface area by epsilon naught, right? But now this is the field that is outside the spherical shell. Inside the spherical shell, the electric field is 0. So suppose you want to calculate work. We did the integral of basically going from A to B, E dot dl. So this is a path integral. So that means when you're trying to find out work, you have to do path integrals where you're going from A to B, and you have integrals like this, E dot dl. But if I were to go from inside the shell to outside the shell, there is some charge in between that is not being considered. right? So at the boundary, which electric field should you consider for this integral? Should you consider the electric field inside to be 0 or electric field outside which is not equal to 0? So we will see in a minute that to avoid this problem, we essentially consider the average electric field inside and electric field outside. We consider the average to compute this integral. So that average electric field is half of this. So the average electric field is sigma by 2 epsilon naught, because E is equal to 0 inside, and outside you have sigma by 2 epsilon naught. So, and factor of half comes from two entities, right? So then if I want to know what is the work done or what is the energy in compressing the shell of radius small r to r minus dr, then that would be equal to essentially the total charge times the average electric field, right? And the total charge here is sigma times 4 pi r square. That's the total charge on the spherical shell, where sigma is the charge density, and average electric field is sigma by 2 epsilon naught, right? And so this is the E average. So you can see that there is an extra sigma here. So you could do another 2 epsilon naught and multiply this with a 2 epsilon naught. So this 4 pi epsilon naught gives you 1 over k, and the sigma by 2 epsilon naught and sigma by 2 epsilon naught give you E square, E average square. So that's how you can see that the total energy density goes as E square here. So now that said, so what we have discussed so far is we looked at what is the energy or density of an electric field. So we came up with this, that it is half epsilon naught E square d tau. And we looked at one specific problem where there is charge at the boundary. So we need to worry about what are the boundary conditions, right? We simply, for now, we fix the problem by considering the average field, but we have to look into more detail there, but we'll come to that. Before we go there, let's talk about conductors. So conductors, usually when we talk about metals, most metals are conductors. These solids have a specific lattice structure. The atoms are sitting in a specific configuration. So you have this atomic lattices, right, where atoms are essentially sitting on the edges, and they're ordered. So inside a solid, all the atoms are ordered in a specific lattice, and you will have to go later when you take quantum mechanics, or if you have already taken quantum mechanics, you would see that you can consider the potentials from each atom here, and you can look at their interaction, and you can from a very simple analysis you can come up with what is called the band structure that describes how the energies of electrons are distributed within the system. But to understand it from a very simple standpoint, which is in a way oversimplification, but we're actively turning off these quantum mechanical aspects for now because we are dealing at length scales and time scales that are much bigger in electrostatics. So what we are going to do is we are going to consider a conductor as having a sea of free electrons. So these are not, these are very loosely bound, if you want to think about it that way, to their atomic nuclei. So if I have a conductor, let's say this is a piece of a conductor, and I place it in some electric field. So I place this conductor in some electric field E. Now what happens is that you would get these electrons, these free electrons which are within the conductor would move in response to electric field. After all, electric field means in the presence of the electric field, any charge gets impetus or momentum to move. So the negative charges, the electrons move to the side. Because remember that the force is QE. So for an electron, it would be opposite. It would go this way, opposite to the field direction. So there are more positive nuclei that are left here. Because of the nature of the atom, the protons are much heavier than electrons, although their charge is exactly equal and opposite, but their masses are very, very different. And because the protons have a lot of mass, they don't do much moving because this force is equal to QE is equal to m times a. That's the acceleration you would get. So the acceleration you would get is QE by m. So for protons, this mass of protons is high, so their acceleration is low. On the other hand, mass of an electron is low, almost there is a difference of 1850 times. So the electron does most of the moving here in this case, although they feel the same force because the electron is much lighter. But anyhow, there is what you call as dipole moment here now. So while studying the multipole moments, we did talk about dipole moments where you have two charges separated from each other, right? So now there is a field because of these dipoles within the conductor, right? So the conductor has a field, and that field goes like this. And if you want, you can quickly go back to the multipole expansion to see what the potential should be, right? Recall that potential at a point R2 due to a dipole would be 1 over 4 pi epsilon naught, the dipole moment times R by R cube. Right? So essentially you have a dipole field here inside. So this E1 and this, let's call this E0, that's the applied field. So this E1 acts so as to balance out this E0. So there are charges that accumulate on the surface so that the electric field, the total field inside the conductor is 0. Now, another thing that you have to consider is that when you apply an electric field, for example, there is no electric field to begin with. If I plot electric field as a function of time, so let's do this on the next slide. So I place a conductor here. This is a conductor. So let's call this electric field, and this is time. So there is no electric field here, and at some time t is equal to capital T, I turned on the electric field, right? So I turned on the electric field. Obviously, when there is no electric field applied, the electric field inside the conductor is 0. But at time t is equal to capital T, I applied this, I switched this electric field on, I dialed the knob up, then the acceleration of the electrons is going to be QE by m, right? And you can see, from the electron mass and electron charge, and you can take roughly some 10 volt per meter or 100 volt per meter electric field and see what this acceleration would roughly be for an electron, right? And you would see that for the time scales that we are considering, the electrons moving from their atomic nuclei to the surface, the time taken for that is much lower. It's much lower than even a nanosecond. So in fact, it can even go down in some solids to picoseconds and femtoseconds. So it depends obviously on the conductivity and the properties of the material, but for the time scales, we are considering time scales of maybe milliseconds or microseconds. So for those time scales, for pretty much those time scales, you can consider that this process happens instantaneously, so that as soon as you apply an electric field, you can think that these charges instantly move and the electric field inside is zero. We're presently studying electrostatics, so we're not going to go into the oscillation of these electrons themselves directly right now, but we will do that later in this course. So overall, an electric field is set up within the conductor such that the applied field is cancelled, so the total electric field is zero in a conductor. And so all the charge resides on the surface of the conductor, like we have just seen. So the electrons and the leave this thing and go here, so they go to the surface. And because there is no electric field inside a conductor, that means if I take a point A here within the meat of the conductor and point B here, there is no electric field. That means the potential at A is equal to the potential at B, or we call the conductor as equipotential. Right. And then finally, because the charge, suppose if I have a conductor like this, right, and the charges, the negative charges, come out to the this is not a boundary, these are negative charges that I'm drawing here. Negative charges come out to the boundary, right? The electric field is perpendicular, right? The electric field is perpendicular from the surface. So at any point on the surface, the electric field is perpendicular to that. So electric field is perpendicular to the surface. So now let's talk about a conductor where in the core, you can cut out a cavity. So if I have, imagine a three-dimensional conductor, right? And inside it, I cut out a cavity. So this is a cavity that I'm going to drill in and cut out that piece and take it out, right? So now if you put this in an electric field, what happens? If you put this in an electric field, still same thing happens. Negative charges come here, right? And then you would have um, positive charges here on this side and negative charges on the inside, right? And the net electric field inside here would also be zero inside the cavity. And the field lines would go smoothly through the cavity, but E will still be zero. So if I place a charge here, if I place a charge in the cavity, then that charge is shielded from this external electric field, because the charges on the metal redistribute on the surface here to shield whatever is inside this cavity from the external electric field. So if I have a cavity in a conductor and there is a charge in that cavity, it is shielded from the external field, because the external field is cancelled out by these electrons moving to the surface, and because of that motion, the electric field inside the cavity is cancelled, and that's the essential concept of Faraday cage. So many sensitive instruments are often put inside a Faraday cage for this reason, to shield them from stray electric fields. Okay, now let's get back to the thing that we asked while discussing a spherical shell. So we asked about what about the boundary conditions, right? What about if we encounter some charge? So to do that, let's look at force on a conductor. So if I just take the surface, if I take a conductor, let's say, right, the surface gets charged, right? all the charge resides on the surface, but E inside is equal to 0. So the net charge is essentially a surface charge distribution. It's like a sheet of charge that we talked about, right? It's like a sheet of charge here, right? Because the E inside is 0. The only thing that can produce charge is on the surface. So I have a surface charge distribution. And we looked at what is the electric field of a surface charge using Gauss's law. If you recall, we considered the Gaussian pillbox for this. So we had a Gaussian pillbox above and below the the surface charge, and the side faces canceled out, and from the top and bottom faces we were able to get that the electric field is equal to sigma by epsilon naught along n, right, where n is pointing up when you're at the top and below when you're at the bottom, right. Now we know that this E is equal to the gradient of V. So in this case, we have the n vector. So the gradient of V is essentially along minus dou V by dou n, right? Dou V by dou n along n is equal to sigma by epsilon naught n, or sigma is equal to minus epsilon naught dou V by dou n, right? So there is electric field here. So in the presence of this electric field, the charge will experience a force, right? And let's look at how this would happen. So to do that, if I consider this sheet of charge, let's consider a small patch here. So this small patch, let's say it has the surface charge density of sigma, right? So then here I have, because of this patch, so because of this tiny patch, I have sigma by epsilon naught going up and sigma by epsilon naught going down. Now I want to see the force experienced by this patch of charge. So I can write the total electric field. Let's call this the patch and this call it other. So the total electric field that is there is coming from both the patch plus rest of the sheet. Patch cannot exert a force on itself. The electric field that is being produced from this patch cannot exert a force on itself. It is coming from there, right? You cannot pull yourself up to fly. Similarly, this charge, this patch, the electric field from the patch is not contributing to the total force that is acting on the charge within this patch. It's the we have to consider only E other for calculating that force, right? So if I look at E total above the sheet, I have E coming from rest of everything, E coming from other, that is rest of the sheet other than the patch, but the patch electric field is pointing up. If I look at E total below, then E other minus sigma by epsilon naught. But to calculate the force that is on the charge which is located within the patch, we need to know E other. So I can write this from here. If I add these, right, these terms cancel out, and I get twice of E other is equal to E above plus E below. Or this 2 goes there and you get an average. And that's what we were discussing when we talked about the electric field inside the conductor, inside the spherical shell versus outside the spherical shell. There also we had taken an average. And that average comes from the fact that here, as you can see here, the patch itself cannot exert a force on itself. So it is the rest coming from the other contribution, which by using the simple equation, we can write as an average of above and the field below, right? So this average field then is equal to, So inside the conductor there is no field. Outside the conductor there is a field of sigma epsilon naught. So the average field is sigma by 2 epsilon naught, right? So that gives us the average field. So E average would be sigma by 2 epsilon naught, pointing along n. So then we can write what is the force per unit area. Force per unit area, which is equal to the pressure, uh, um, which gives rise to the pressure, would be the charge itself times the electric field. This is charge per unit area. That's why we are getting force per unit area. So that would be sigma times sigma by 2 epsilon naught, right? So I can write this, I can add another 2 epsilon naught and multiply it with another 2 epsilon naught, right? Then I can write this as sigma square by 2 epsilon naught whole square times 2 epsilon naught. So I can, this is nothing but essentially uh, E square, right? So so from there we can see that the force experienced by the patch or the charge in an electric field would also be proportional to the term E square. So we'll stop here, and in the next lecture we will discuss capacitors.